Hello all. Welcome to the supplementary material of Leibniz philosophy, where we try to understand his pluralism and focus on individuality through the example of definite integral as limit of sum. Uh, you all might be familiar with the formula, but let us just correlate all the elements according to Leibniz monadology and his philosophy. So let us consider Leibniz's space-time. So we have space and we have time here, and we have an arbitrary universe that we have imagined in Leibniz philosophy. For simplicity, let us just have a finite kind of universe here defined by a and b, the limits, and our aim is to understand or conceptually cover the area of this entire universe. So let us try to understand how Leibniz would have approached this problem. A very simple approach for people who are familiar with calculus. So we know that the area of any known figure to us, any known geometric figure to us, like a square or a rectangle, is nothing but the product of its dimensions. So we have a and a in terms of square, which is a square, and a and b, we have the area as ab. So let us explore the area of any area under any arbitrary curve like this changing curve through the lens of our known geometric figures and their areas. So this is how Leibniz himself propounds his philosophy through indivisible arbitrary elements, which he terms as monads, and he also accepts the plurality of monads. So it is not just one monad which is morphing or evolving into another monad, and we have seemingly plural monads which are actually reconciled into one single substance, and the others are just forms as expounded by Spinoza. That is not the route that Leibniz takes. He takes a basic indivisible structure from where he starts to analyze the whole picture, and he also accepts the plurality of such substances, and we will see the significance of the plurality of the substance and the simplest element that we have taken in our hypothetical problem. So in a ever-changing universe, let us just consider an arbitrary curve like this, and we will try to solve the area under this curve through the concept of parts of a whole, parts which make a whole, analyzing the parts, analyzing the whole as a kind of a sum of its parts, or to be specific, limit of the sum of the parts. Limit because we are never exact in our estimation, and we will have to resort to making one of the dimensions of the parts tend to infinity, and as it increases, so does our accuracy, and this is the limitation. So let us begin with a very simple visualization here to analyze the area under this curve. This area under this curve is not anything like we have seen before. It's not a defined or definite shape, hence we will have to resort to the process of estimation. And let us start or begin our estimation with a basic kind of a rectangle here, and with estimation comes deduction, and with deduction comes iteration, with iteration comes evolution, and these are some common terms that we see in Leibniz philosophy. And we see dynamism that comes with the process of estimation, we have continuity that comes with the process of estimation here, and we can see that some of the core concepts of Leibniz philosophy can be invoked to solve our example problem. So let us first consider a rectangle whose characteristic is the length and the width, and let us try to just find the area under this particular rectangle to estimate the area of under this arbitrary curve. Let's call it curve 1. So we can see that we have just estimated part of the area of that curve, which brings us to Leibniz. In Leibniz's own words, it is limitation of representation. We see in his philosophy that he propounds the principle of continuity and activity of monads, where he says that the two properties of reflection and representation. By reflection, he accepts that each and every monad is a reflection of the entire universe, and by that we can infer that each and every rectangle or any shape that we are going to assume also has the same characteristics or the basic dimensions of the curve that we have imagined, which is x comma y. In our two-dimensional example, it is nothing but a constituent of the two-dimensional space and time which we have assumed here, and by nature or by essence it is representing a two-dimensional geometric figure, but by representation it is not. They have varied representations: a rectangle with a broader width, a rectangle with a smaller width, and so on. So their representation brings the unique feature of diversity in them and the notion of plurality, and we will just explore how this this diversity is going to help us piece the whole together. So unique set of rectangles are going to help us find the solution to our problem of the whole, and this is basically Leibniz philosophy through the lens of mathematics, or one of the concepts of mathematics, real analysis. And here we see that this is a very weak estimation that we have resorted to. We have not estimated the area of this portion, and therefore this estimation is weak. Now let us get into slightly a stronger kind of estimation, where we take another rectangle here. For example, let us consider the other rectangle, and now you can see that this is a slightly better version of our estimation, but this area has been neglected again. And by logically extending this kind of methodology, we finally come to a conclusion that we have to resort to a technique of employing multiple set of rectangles, such as the one shown here, to successfully estimate our curve, or the whole, as we would like to consider. And here comes the estimation. So here we have our basic and finite elements with the same property, reflecting the same property as that of any curve in our two-dimensional universe, but with varied representation. So here we have our basic elements. We have rectangle 1, and we have 2, we have 3. We have done nothing but we have split the entire area in terms of parts to represent the whole as a sum of the parts. The caveat here is that we are resorting to extremely small parts, and this is the essence of Leibniz philosophy, where he says that monads are nothing but the smallest indivisible elements of the universe. And why so is because the smallest and indivisible elements themselves can actually aid us in representing any whole as a sum of the parts. So The smaller you make it, the more precise your understanding of the universe, and which is why he adopted the definition of indivisible parts. And this height is varying in our rectangle, which is why we say that the reflection is same, or as in they are by essence they are two-dimensional geometric figures, but by representation they are different. For us to tie into the concept of unity in diversity, or represent the whole as a parts of the sum. So we have the same h all the time, and we have the height varying as a function of our hypothetical universe, which we have to understand the area of under our curve. So let us place our rectangles starting from the coordinate a, and with of course varying heights. We'll not get into the intricacy of the difference in the left and right limit, and we will just consider the left hand side height and varying as a function of the curve for our example, and we will try to make it as simple as possible here. So we have the basic area of a rectangle is our height into width, and in this case we have seen that width is h, and let us just denote height with the hi, and we will see that the curve is a function of, so an arbitrary function f of x. We have seen y and x here, and we can see that the height of our rectangle is changing in accordance with the shape of the curve and as a function of f of x, and we will just have to plug in the value of x at that point, or x coordinate of that point, to get the value of our y. This is y at that particular point, or height at that particular point. So at this point we will plug in the value of a, and we will get y is equal to f of a. So when we do this, we have the area of our first rectangle as f of a into h. The area of our second will be, and we can see here that this is incrementing by area of h, and this is a plus h. And this, as we move on, at b we will finally be at a arbitrary value of a plus n minus 1 into h. So at the second coordinate we have a increased by a infinitesimally small amount of width, which is h, into the width itself, and finally at an, or the point b, this point a and this point b in the graph, there we will have f of a plus n minus 1 into h. And when we tie all of them together, and we want to represent diversity through unity through diversity and make the whole as logical parts of the sum, therefore we will have to tie up the parts, individual parts together, and since they are made up of infinitesimally small parts, let us resort to integration, and at the end we can conceptualize that the area under the curve, or our hypothetical understanding of the hypothetical universe, is nothing but a sum of our individual understanding of elements, and the representation is just a summation of all this. So we will have to take some terms common here, like the height, which are repeating, and we will make that a constant, and we will just not care about that constant. We'll call it some arbitrary c, and we will see the final equation in terms of proportionality only, and we will avoid this constant in our final equation, as we have invoked the proportionality sign. Here we have our final area or understanding of our hypothetical two-dimensional non-changing static universe, so as to say, to make it simple, as a sum of the parts. Here are the parts, that we have seen f of a plus h until f of a plus n minus 1 into h, that is the area of our individual rectangles, and in this case we are considering rectangles as our monads, which Leibniz has labeled. And since the rectangle has to be ideally, its properties are very similar to monads properties, that is infinite in number and infinitely small. So only then we get a clear and very precise picture of our universe if the width of our rectangle is infinitely small and the number of such rectangles are infinite in number. So this is a direct statement from Leibniz's philosophy, and we have the sum of our areas of our individual rectangles here, and the final area is proportional to that sum with some constant which we have taken common, that is with respect to our height, which is common, and I've just negated that constant by making it proportional for this example. And here we invoke Leibniz's concept of obscurity and movement from obscurity to clarity. And this movement is Leibniz's explanation of dynamism through the aid of individualism and pluralism. Pluralism because all the rectangles are individual and real, as real as the whole themselves, and they are unique with respect to representation and common with respect to reflection, or they are all two-dimensional geometrical entities of similar type, but their representation is different as they have varying lengths. So the obscurity is when we have our number of elements as low as possible and our width as high as possible, and we move to a state of clarity when we have our number of elements as infinite and our width, or the physical dimension of our element, as completely zero, or occupying no space-time at all in the term, in the words of Leibniz. So we move from a state of obscurity with respect to our understanding of the universe. Our understanding of the universe, our hypothetical non-changing two-dimensional universe, is the area under our curve that we have assumed, that is our universe, our understanding of our universe. And the understanding is very obscure when we have very small elements to make up the whole, or when we assume only a very small amount of rectangles to understand the area under the curve, and also when the dimension of our smallest element is extremely large. That is the state of obscurity. And we move to clarity as and when our number of elements are increased to infinity, so infinitely in number and in height or width, it tends to zero, or it is infinitely small, infinite in number, infinitely small. That is when we move to the state of clarity. So this explains the dynamism that we see in his philosophy through pluralism and individualism. And this is how he ties unity with diversity and represents the whole as a sum of the parts with, of course, the limit of some example that we will see. As seen with the previous example of the limit of sum, we had considered a very simple example, and the things change as and when we consider a multidimensional expanding kind of a universe. So does our area under the universe, or what I would like to term as our understanding, become more and more complex, involving multivariable calculus and differential equations of different orders, with forcing us to invoke some kind of mechanism to solve differential and then integrals and such complex vector calculus and so on. So that is just an expansion of our basic example that we saw, and to also give you a hint about pre-established harmony, let us explore a small video that explains the example of a particle pair and the ghost nature of spin between a particle pair.
The apparent implication is also that when the spin of one particle is measured, it sends an instantaneous message to its partner to spin in the opposite direction. If each particle makes up its mind about what direction it's spinning only when it's observed, then we need this instantaneous message from one particle to the other in order to guarantee that the two particles will always decide to spin in opposite directions when the detectors are aligned. This is true no matter how far apart the two particles have traveled away from each other. Even if we wait until the two particles are on opposite sides of the universe before we make our observation, this instantaneous message still seems to occur.